So he's a postdoctoral researcher at UC Santa Barbara now. Earned his bachelor's from Poerschke, and he was PhD at UC Santa Barbara as well, working in Carlos Levy's group. And his research focus is on thermodynamics and kinetics of structure, distribution, and multi-phase materials. We're talking about ionic substitution at height.
Great. Thanks for the kind introduction. So I hope that while you've been waiting for the seminar to begin, some of you have noticed this microstructure. I think it's quite striking. You see these elongated, highly faceted grains, some of which are almost perfectly hexagonal in cross-section. These are grains of a phase called apatite. The hexagonal crystal structure represented by this general formula shown here. The structure is made up of these covalent tetrahedra, and the arrangement of those tetrahedra produces two distinct cation sites, one 7-coordinate and one 9-coordinate, that are arranged as columns along the c-axis of the unit cell. There are also these anion sites located in the center of this ring of cation sites, and we can put a variety of atoms into these different sites, different sorts of tetrahedra, different cations into these sites, leave some of these empty, fill them up, and based on how we change the population of sites in the crystal structure, we can enable a wide range of potential applications. I come from a group that works on structural materials, and so I think I should probably start with a structural example. And at a deeply human level, apatite is probably the most important structural material there is because it makes up much of the mineral component of our bones, more than 90% of our teeth. If it weren't for apatite, I couldn't stand in front of you here today. And in this case, the tetrahedra are primarily phosphate groups, and we fill up all the cation sites with calcium atoms and put some hydroxides in those anion sites. And we can change slightly the makeup of this. So if we consume fluorine in our diets and our drinking water, a little bit of fluorine substitutes for some of the OHs and improves the acid resistance, improves the quality of our teeth. A nice, bright smile without cavities. The problem is that when we put too much fluoride intake, the chemistry changes, and instead of improving the properties of the teeth, can lead to pretty significant dental and skeletal issues. So there's a balance here. And one of the challenges is that in some places in the world, there's a lot of fluoride naturally in the drinking water, and so we need to get rid of that in order to prevent these sorts of issues. Here in the US, if you have a water source with a lot of fluoride, you go to our friends at GE and buy one of these electrodialysis systems, and that takes care of the problem. But where I first became acquainted with the problem was working with Engineers Without Borders while I was in graduate school. And we worked with a community in Kenya where this was a big problem based on the local geology and the makeup of the soil. And the community, the setup of the community could support an industrialized system like that. And so we had to come up with another solution. We worked with a nonprofit organization that works in this part of Kenya. And the solution that they've come up with are these absorption filters. They use some calcium phosphate to absorb the fluoride, but the really magic material is this stuff called bone char. They take cattle bones, they heat them up to high temperature in a slightly reducing environment. In the lab, we'd call that pyrolysis. And they end up with a very finely porous, high surface area material that turns out to be very good at capturing the fluoride present in the water. The same way that our bones would absorb it, and it would degrade the bones, instead, this bone char material absorbs it, and it solves the problem. And so we worked with this community to implement some of these filters, and it works. So this is the fluoride level when we started out. This is the drinking water standard from the World Health Organization, and after we installed the filter, the fluoride levels dropped quite a bit. So this is sort of an example of, we wanted to prevent the absorption in the body, and so using the apatite structure that's present in this bone char material to absorb the fluoride beforehand, so we don't end up consuming it. So if we, instead of using the phosphate groups, if we put silicate, germinate groups in the tetrahedral sites and a combination of alkali earth and rare earth cations in these cation sites, fill up the anion sites with oxygen, we can produce some functional materials. They've been used as phosphor hosts, studied as oxide thermoelectric materials where the low thermal conductivity is really advantageous. And the final example of what I'm going to spend most of my time today talking about is the role that apatite plays in this coating technology that Pratt & Whitney calls a non-stick barrier for their jet turbine engines. And you might think non-stick, a frying pan or something, but the temperatures and environments that they talk about here are well above 1,000 degrees Celsius. And it turns out that the secret to how this non-stick barrier works is apatite, and the fast crystallization of apatite and the flexibility in terms of ionic substitution and the range of cations that can go into that structure. And so I'll talk most of the rest of the time today about this application. Before we get to that, I think it's useful to do a quick primer on turbine engine operation and what some of the challenges are. So this is a basic schematic. Air comes in the front, it's compressed to very high pressure, fuel is injected and burned, and then as the hot gases leave through the back of the engine, they power a turbine that both drives the compressor up front as well as this big fan that sits at the front of the engine that provides the forward thrust. We like these to be as efficient as possible to keep our ticket prices down and reduce the environmental impacts. And the big challenge in that are the materials. So if we think about where the adiabatic flame temperature is for jet fuel, it's up here above 2,000 degrees Celsius. We need to build the engine out of something. And the conventional material of choice have been these nickel-based superalloys. And this shows roughly the evolution of the temperature capability of those materials. We see that there's a big gap. And so the way that that gap gets filled in conventional engines is with cooling air. We divert a lot of the air from the compressor after it's been compressed and dump it into the combustors to dilute the combustion gases and bring the temperature down, and use it as forced air cooling and thin film cooling in the hot section components to keep their material temperatures down. So anything we can do to close this gap ultimately improves the efficiency of the system. And one of the strategies that has been employed for about 3 decades is the use of these so-called thermal barrier coatings, or TBCs. They're ceramic coatings that go onto the surface of the superalloy components and enable a more efficient use of the cooling air so we can increase the material temperatures. And there's a lot of work being done in this area to try to increase the temperature capability, both of the alloys as well as the coatings, so that we can continue to close this gap. At the same time, there have been parallel efforts to implement more ceramic structural materials, these so-called ceramic matrix composites, to replace the superalloys. They also require coatings, less for thermal protection and more for environmental protection, to prevent interaction between the combustion gases and the ceramic material. And so the development of these coatings is focused on slightly higher temperatures and a different set of challenges, but again, we require ceramic coatings to protect the material in surface. And there's been a lot of progress in this sense. And one of the challenges that has emerged as a result of that has to do with the environment in which these aircraft operate. It's not always a clean environment. Military aircraft often operate in desert environments on improvised runways where there's a lot of sand and dirt in the air. Commercial aircraft often have to contend with either strong or even dilute volcanic ash concentrations in the atmosphere. Remember back a few years ago to when the airspace between here and Europe was shut down because of the volcanic eruptions in Iceland. And the issue that's associated with all of this, dust, sand, dirt, volcanic ash, etc., is that the engines are now burning hot enough that when this goes into the engine, it all melts. And it sticks to everything in the hot section of the engine. Basically, you take the volcanic ash, turn it back into magma, and you've got magma coating the inside of your jet engine. It doesn't do a lot to help the durability of the system. We return to these 2 different types of coating materials. The thermal barrier coatings that are used on the metals generally have a segmented microstructure. And that microstructure is used to provide strain tolerance or create a more compliant microstructure so that as the system gets thermally cycled up and down, it helps compensate for the thermal expansion mismatch between materials. And in this case, the issue is that we have this liquid, this silicate, basically liquid glass on the surface of the coating, and it's driven by capillarity deep into the coating. And then it freezes, it stiffens the coating, and the coating eventually falls off because of the increased strain energy upon thermal cycling. For the environmental barrier coatings, these are the things that we put on the silicon carbide-based composites. The issue is more in a classic corrosion type problem where the coating material starts to dissolve into the melt. We get different phases that have different properties, and ultimately that leads to accelerated failure of these coatings. So in this case, our goal is to keep the the liquid from penetrating, this molten deposit from penetrating into the coating, and we can do that by producing reactions between the coating and the melt to block infiltration. And in this case, we'd prefer if there were no interactions between the coating and the melt, so that basically the melt or the deposit just sits on the surface and doesn't interact with the coating. So sort of different design goals, but because of similarities in the materials, they're both rare earth-based materials, some of the understanding crosses over between the two different coating types. So if we focus first on this TBC application where we have a segmented microstructure and the issue is the penetration. We can do things like calculate based on the viscosity of the liquid how quickly a coating might be penetrated, and we find that that's in the span of minutes to hours, much less than the lifetime of these components. So obviously, if the melt is there, it's going to penetrate. And as it penetrates, if we look at the energy release rate, this is the stored elastic strain energy in the coating as the melt penetrates, or after cooling of a penetrated coating, that this energy increases pretty dramatically with the penetration time. It's more than a linear increase. And the toughness of these coatings, depending on the exact microstructure, probably falls somewhere in here, which is to say if we penetrate more than about 100 microns or so, the coating will fall off upon a subsequent release cycle. So how can we prevent infiltration? For the conventional material, this YSZ or yttria stabilizer zirconia material that has long been used in this application, there isn't a lot of interaction between the coating material and the melt. And so the only hope of preventing infiltration is the fact that we have a steep thermal gradient through the coating. And we might hope that as the melt penetrates, it will drop below its solidus. And if the nucleation is fast enough, we might crystallize the melt for some of these phases. These are all mineralogic or geologic type phases, and that might block the penetration. And it turns out, though, that the time required for that to happen, for the nucleation and growth, at the undercoolings that you might expect in the coating, it just isn't fast enough. And so these materials are really susceptible to this mode of degradation. So one of the solutions is to increase the rare earth content. Instead of yttria stabilizer zirconia that has 7 or 8% yttria, we increase the rare earth content up to maybe 50%. And this is where apatite comes into play, because it turns out that the nucleation and growth kinetics for apatite are incredibly rapid. So as some of this rare earth containing coating dissolves into the melt, it reacts with the silicate and the calcium that are in the melt. And if we remember back to some of the apatite compositions, these are calcium or alkali earth silicate based materials that have a lot of rare earth in them. And so this interaction within a matter of seconds, after the dissolution happens, we get apatite precipitation, and with the growth morphology, this sort of faceted needle-like morphology, it very quickly fills the gaps in the coating microstructure where the melt is penetrating, and the penetration stops. And so, in this case, this is something that you can see in 4 hours at temperature, and the penetration is just a few tens of microns instead of hundreds of microns that we would expect in a typical coating. So, again, apatite is the key to this process, the fast nucleation, the fast growth. But the process doesn't work equally well. Rather, I should say here, so this process works. So this is an example from a jet engine, a Pratt & Whitney engine, where these are our turbine blades that had the conventional coating on them. They flew in a harsh service environment, probably an airline operated in the Middle East, where there's a lot of sand coming into the engines. And this coating, these big regions are places where there's bare metal exposed. The entire coating has been lost. The coating on these blades is this gadolinium zirconia. The base system has a lot more rare earth in it, and the apatite crystallization within the structure prevents the infiltration, and the coating survives, even though the toughness of the gadolinium zirconate is a bit lower. But the problem is that it doesn't work equally well for all rare earth cations. It works really well for gadolinium. If we substitute yttrium, we get some penetration, a few tens of microns instead of just 10 microns. These coatings would probably survive. But if we switch to ytterbium, which is of interest, we start thinking about trying to lower the thermal conductivity, or if we want compatibility with different types of coating systems underneath, the process doesn't work at all. So obviously, there's some effect of the change in the rare earth cation radius on the effectiveness of the reaction process. And it's probably a combination of both the phase equilibria, how stable the individual phases are, and the kinetics of apatite crystallization. What's the driving force to get apatite to precipitate or crystallize? We switch now very briefly to the environmental barrier coatings, where we remember that we want the opposite behavior. We want very little interaction. What we find actually happens if this is a big pool, basically, of this deposit on the surface of a coating, progressively in just a matter of minutes or hours, the coating is converted to a mix of liquid plus apatite. And the apatite has a CTE that isn't as well matched with the substrate, and so as the thickness of this apatite plus liquid layer grows, the thermal stresses upon cooling grow, and eventually you get to a point that you get cracks to the coating that bifurcate and end up into the underlying structural material and cause pretty significant issues in terms of the long-term durability. And so in this case, we'd like to understand what drives the apatite precipitation reaction so we can prevent it from taking place. And another approach might just be if we have a TBC material that works pretty well in preventing this mode of degradation, we could just apply an extra layer on the surface to basically protect the coating that protects the underlying structural component. But one of the challenges in designing these coatings is that every aspect of the degradation process, and the viscosity, which influences the infiltration rate, the chemistry which influences what phases are going to crystallize and at what temperature they'll crystallize, it all depends on the composition of the deposit. And these systems, these aircraft, fly all over the world, where the composition might vary on a day-to-day basis. When they fly into an industrial city where there's a lot of sulfate-type pollutants in the environment, that might change the behavior. The next day you fly into a region that has much more sandy conditions, and that might change the behavior. And we can't test every possible deposit or CMAS. These things are called CMAS because they're composed primarily of calcium, magnesia, alumina, and silica, the main constituents of the Earth's crust. We can't test every possible scenario. And there are too many different variations in terms of coating architecture and behavior. And so what we need are tools that allow us to couple an experimental understanding of the phenomena with this bigger picture problem of variable composition, variable surface conditions, and then use that as a tool to design better coatings. So the approach that we've taken to do this is illustrated here. What we'd like to have some library of representative deposit compositions, maybe of different volcanic ashes around the world, or the different types of desert environments that military planes might operate in, and a library of candidate coating materials that we might use to prevent this mode of degradation. And if we had a thermodynamic database that we could use to then calculate what's the equilibrium between these deposits and the candidate oxides and understand all of these parameters, maybe we could either guide the experimental process, so we do the right experiments to understand the degradation process, what conditions are going to be most severe, as well as guide the selection of the best coating material for a given application. And the way that these thermodynamic databases work is this approach called CalFAD, or the calculation of phase diagrams, where ultimately what we'd like to have is a Gibbs energy description of every phase in the system. Be this a ternary system or a 7 or 8 component system. And we develop that understanding of the Gibbs energy of each phase using a combination of thermochemical data, measuring heat capacities, enthalpies, etc., as well as an understanding of the phase equilibria. Because ultimately, the phase equilibria phase diagram is just a representation of the interplay between the Gibbs energy of the various phases in the system. And so we can use both of these types of information in sort of a fitting approach to take a stab at understanding what the full Gibbs energy description is for a given phase. And so the process that I'll talk about today is first efforts to understand the phase equilibria in the relevant subsystems. What are the reactions that take place between these deposits and the candidate coating materials? How does the apatite stability change as a function of the composition of the system? We can then use that to help refine and validate the databases that are being developed in parallel. And then finally, I'll provide a couple of quick case studies on how we've used this tool once it was developed to be able to understand the reaction processes and the relevant variables in greater detail. So we know that apatite is important to the process. The crystallization of apatite is ultimately what we'd like to understand. So we can start by trying to map out where apatite is stable, what range of compositions. when we look at the crystal structure and the allowable substitutions we can do in the crystal structure, we find that we can have a range of compositions that extend over this range, where this is the nominal initial composition. If we go in this direction, which involves putting more calcium in, we have to introduce anion vacancies and anion sites to maintain charge balance in the structure. If we go in this direction, which is taking calcium out of the system, putting more of the rare earth into the system, we can follow two paths. One might be by incorporating cation vacancies, leaving some of the cation sites vacant to balance the charges we remove calcium. Or there's been some suggestion maybe you could put anion interstitials in, stuff additional oxygens into the center of that column of the cation sites to also balance charge. And then the question is, if this is the allowable range based on an understanding of the crystallography, what is the actual stable range relative to competition to crystallize other phases? And so to do that, we need to then consider the phase equilibria in the broader system. And one of the important systems ends up being the silicate calcium rare earth system. Apatite sits here. In this case, there were a variety of other ternary phases that had been suggested in the literature. But what we were after really is what is the stability range of apatite? And so if we map our understanding of the potential crystallographically allowed stability range onto the phase diagram, we imagine that the apatite phase might sit somewhere in this range. And the next step is to determine where the limits actually are. So if we start by making a composition, just wet synthesis to prepare a specific oxide composition, it sits basically right where the end of the apatite field should sit on this silica yttria biline. We can anneal it at a range of temperatures. This is a range of temperatures where it was suggested apatite might be stable. And in fact, we don't see apatite at all. We see disilicate and monosilicate. And I come back to this idea that there had been a suggestion that maybe apatite turned up out here. And in fact, it turns out that the apatite phase loves to pull impurities from the environment. And so if you take a composition like this and anneal it in a dirty environment, a workhorse box furnace that has seen a lot of stuff, it'll pull enough impurities from that environment that you can start to form apatite. But you get a three-phase mixture then, breaks the Gibbs phase rule if you just have a binary composition. And so we know then that can't actually be correct. So if we do the experiments in a really clean environment, we can get what I think is the correct result, which is just a two-phase mixture of these two phases, no apatite. Now, if we intentionally introduce that impurity, that alkali earth impurity, in this case it's calcium because that's the system we're interested in, just put 1% in, now apatite starts to show up in the microstructures. And so we can go in and measure the composition of that apatite and identify this as a three-phase triangle that captures the terminal composition of the apatite phase in this direction. We can then go in the other direction, prepare a composition out here that corresponds to what would be the calcium-rich or the anion vacancy stabilized form of apatite. Again, we don't get single-phase apatite, we get three-phase mixtures at both temperatures we were investigating in this case. And with that, we can then map out where the terminus would be here, and then map that back onto this schematic that shows more directly the influence of the different ionic defects that enable this range of compositions. And what we found down here, first is that the gadolinium system covers a wider range of compositions, and this is consistent with thermochemical data that shows that the gadolinium-based apatite phase is more thermodynamically stable than the yttrium-based phase, a wider range of compositions. And at this end, we prepared apatite or two-phase mixtures on both sides of what this range would represent, and we find that they both fall pretty closely here. So we could use that insight to say that it's probably this cation vacancy mechanism that allows the apatite phase to be stable rather than this anion interstitial mechanism. So the next step is to say, well, apatite doesn't exist by itself. It's part of this multi-phase equilibrium, and so we prepare a number of compositions, and we can use that to then fill out the whole ternary phase diagram. We see there's a little liquid field that pops up here, and what we're ultimately interested in for this application of understanding apatite crystallization from silicate melts for jet turbine degradation issues, what we ultimately want to know is what is the equilibrium between the liquid phase and the apatite phase, how much yttria is soluble in the liquid before we get apatite. And in the true systems, the addition of things like aluminum to the system and magnesium to the system drive the eutectic down, you get a much larger liquid field. But it gets complicated to study the equilibrium in a comprehensive sense when you've got 5 different oxide components. But if we go up in temperature, just in this system, we find that the liquid field expands, and we can then map out basically where the boundary of this liquid field is. In particular, what we're interested in is this 2-phase region between the apatite and the liquid. And based on that, we now have some understanding on how readily yttrium substitutes into the liquid phase, and this information turns out to be really useful in fitting these Gibbs energy descriptions in terms of what is the relative energetic effect of dissolving yttrium into the liquid as opposed to leaving it in a phase like apatite. And we can also use a ternary section like this to begin to understand the interaction, or better understand the interaction between coatings and these calcium silicate-based liquids. So this sort of a liquid. We've got a liquid somewhere here. Many of those liquids, as yttrium dissolves, will form apatite. But we also have these fields on both sides, and so the bounding cases would be if we have a really silica-rich liquid, we might crystallize out this silicate, or if we have a calcium-rich liquid, we might crystallize out this silicate. And this is sort of the range of calcium-silica ratios in the typical deposits that are observed in engines. And if we think about dissolving an yttrium silicate coating, this is one of the materials used used for these environmental barrier coatings. We find that initially we might form some apatite, but eventually we'll get to a point that we have the coating materials in equilibrium with the liquid. And the point, or once that happens, we would expect that the coating degradation or dissolution would stop. If we use this rare earth silicate instead as the coating, we find that there's not a shared phase field between the coating material and the liquid phase, and so we would expect that as long as there were liquid still present, as long as there was some deposit on the surface, the reactions would never stop, and we would eventually consume the entire coating. And finally, if we have an yttria source from a yttrium zirconate coating, again, we expect most of the relevant range of deposit would first fall into this apatite field, but if we had a really calcium-rich deposit, we might instead form this silica-carbonate phase instead. And then the crystallization kinetics of these 2 phases are different, and so if we are in a regime where we form this phase instead of this phase, the mitigation strategy doesn't work as well because this phase is much slower to nucleate growth. If we compare this with the gadolinium system, the first thing that we see to make this comparison is that all of these other ternary phases disappear. Only the apatite phase is stable, really extending far out into the ternary. And we also find that for the most part, unless we're basically crystallizing out calcium silicate or pure silica, that any interaction with any gadolinium-based coating material with a calcium silicate liquid is going to produce apatite. And that means that from the perspective of designing materials that we don't want to, or coatings that we don't want to interact with the liquid, we should pick yttria instead of the gadolinium, because the yttria is more likely to eventually get to a point that the reaction stops. But if our goal is to promote apatite crystallization, as it is in the case of the thermal barrier coatings, gadolinium would probably be a better choice because of a stronger driving force for apatite. So the next question is, here we're looking at a ternary system. Does this actually extend to relevant CMAS compositions or the relevant deposit compositions for the application? And so the first question is what is the behavior of the range of debris that we might expect? And so what we've done here is collect information on the composition of a lot of different volcanic ashes, different sorts of sands. These are test dust type sands that the military uses to test their engines, more so from the perspective of wear of components, erosion of components, but I think that they're starting to become more aware of this issue of the melts. And what we've done here is, as a function of temperature, ask the question, how much of the debris that comes into the engine is actually going to melt? Because it's the molten material that's going to stick and is going to cause problems. If it stays solid, it'll just pass through the engine and will be much less damaging. And we pick a temperature like 1200, which is a relevant temperature for today's engines. We see that there's a pretty wide range in terms of how much liquid there is in these systems at given temperature. And we can also say that since it's the liquid that we really care about, maybe we can just back up and come at the question from a different way. Instead of saying, let's characterize all of these different sources of environmental contamination or debris, and say, what are the liquids that can actually form regardless of what the debris source is. So if we back up and just look at, this is a sort of a modified projection of the liquid surface just for the silicate calcium alumina system. These are the components that make up the majority of these deposits. We can say that at 1300, the range of liquids is pretty small. It falls in this little dark blue shaded area. And the range of deposits or debris that would cover is much broader. So if we want to understand the behavior of any deposit or debris that's out in this larger area, we can just pick a liquid that's in here and maybe a few outlying cases. If we start to add magnesia to the system, another constituent that's relevant, we shrink a little bit in this direction of the liquid field and expand in this direction, but again, we can start to map out what range of compositions is relevant to study. And so we picked a few of these, some that fall right in the liquid field and some that fall just outside the liquid field, to use as in an attempt to validate our understanding of the underlying phase equilibrium. So if we look at these systems by themselves, we find that the two, and if we just equilibrate them at 1300, which is sort of a relevant future-looking temperature, the two liquids that were in phase field, or in the liquid field, we just get liquid that quenches the glass. And then we have these two compositions. This one is a silica-saturated system, where some silica actually precipitates out, and this represents one extreme in behavior we'd expect. This is a calcium-saturated system where some suitable astatine or calcium silicate precipitates out, and this represents another extreme in the potential behavior. And the calcium-silica ratio in both of these are the same, and so we see the effect as we add magnesia that the liquid field expands. And so the more complex the deposit composition becomes, the larger the range of liquids that's relevant to study. We can then look at the equilibria with yttria, since this is one of the materials or one of the oxides that makes up a lot of the coating materials that are of interest. One of the things we find is that over this entire range of deposit compositions, large changes in the calcium-silica ratio, apatites don't crystallize as universally. And as I've said, in some cases that's good, and in some cases it's not so great. When we look at these outlier cases that are further from the center of the liquid field, in this case we also precipitate out an yttrium-containing calcium magnesium aluminosilicate garnet. In this case, we get the silica carnotite phase, and in this case, we precipitate out some yttrium silicate. So we've mapped out the extents of the phase field where we expect apatite to form. And if we map these compositions, these experiments back onto this ternary section, we basically captured each of these three phase fields. In each case, we have apatite, but then we also get these other silicates in the system. The next question is, what happens if we add zirconia, since many of the coatings that are of interest are zirconia-based? And what happens in this case is that the coating material dissolves. It's a mix of yttrium and zirconia in the material called delta phase, that particular composition. It dissolves. The zirconia is much less soluble in the melt, and so it reprecipitates as this fluoride phase, which has less yttria, but still some yttria in it. And the rest of the yttria goes to form apatite. So again, we get apatite in every case. In this scenario, the silica activity is actually high enough that we also precipitate out the zirconium silicate or zircon phase. So again, we're trying to understand the limits of the system. If we do the same experiment now with gadolinium, the bottom row is gadolinium, we see first off that the morphologies have changed. In this case, they look pretty similar. We get apatite and fluoride in the glass. But in this case, we no longer see fluoride. It turns out that the zirconia precipitates instead of the crystal phase with almost no gadolinium in it. And that leads to a significant increase in the amount of apatite that we can form, because the gadolinia is going into the apatite phase instead of into the reprecipitated zirconia-based phase. And that's a good thing. We can also look at the composition of the apatite. When we do the experiments just with pure rare earth oxides, either yttria or gadolinium, the apatite composition is basically constant if we look at the calcium content. And this composition right along here corresponds to this defect-free structure where we don't have to incorporate any vacancies to form the apatite. Now, when we do the experiment with zirconia in the system, we find that as we increase the amount of calcium in the deposit, in the melt, the amount of calcium that goes into the apatite increases. And this would be good from the perspective that for every mole of rare earth that we put into the system, we're pooling more calcium out of the system, consuming more of the melt, increasing the volume of crystalline phases, which promotes or better seals the gaps that allow the infiltration to happen. And we see that in this case, there's not much difference between the yttria and the gadolinium composition. Even if there's maybe a greater driving force for the gadolinium to precipitate, the composition doesn't change a lot. And if we look a little bit further, what we find is that this difference between the zirconia-containing cases and those without zirconia is the fact that a little bit of zirconia can go into the apatite structure in the end, and that zirconia charge balances calcium substitution. And so even though we have a range of calcium substitutions, if we add up how many oxygens we have per apatite formula unit, it's about constant. And this tells us that there must be a really large energy penalty for these apatite compositions that involve vacancies to form. And so this also says that if our goal is to produce as much apatite as possible, we really need some of the zirconia there because that's going to facilitate this wider range of compositions that better consume the molten deposit. Come back now to this set of micrographs and talk a little bit more about what's going on the other side of the system. Talk about the apatite composition. If we look at the fluoride, which is the reprecipitated zirconia-based phase that has some yttria in it, we find that as we increase the silica content in the deposit, we reduce the amount of yttria that ends up in the fluoride. And the fluoride is sort of a parasitic phase, and it's just pulling the rare earth back into itself rather than promoting apatite formation. And there's some modest change as we increase the silica content, suggesting that maybe we're increasing the driving force for apatite precipitation as we move in this direction. However, the big difference shows up when we compare yttria and zirconia, in that much less, gadolinium, yttria and gadolinium. In the gadolinium cases, much less of the gadolinium ends up in the parasitic fluoride phases, and it's only in the really calcium-rich systems that the fluoride shows up at all. Otherwise, we basically get pure zirconia back or we form zircon. And this turns out to be an important factor in determining the difference between the behavior of the different rare earth systems. If we come back, to think about the broader context of the influence of the rare earth cation radius, we see a large variation in the composition of the reprecipitated fluoride phase, and as this composition changes, moves in this direction, we can get more and more apatite crystallization for a given amount of rare earth in this system. And this directly explains then the difference that we see between the gadolinium system that falls sort of in the middle in terms of behavior and in terms of rare earth cation size, and these other systems that perform less well in this context. The yttria performs particularly poorly, and that's because the difference in the fluoride composition between where we start and the fluoride we form is very small, so we can't form much apatite in that system. So, we've now kind of built a foundation on what are the relevant reactions to look at, and we can now work on building this into more of a modeling framework. And so, in this project, we worked with this company called Poerschke, which is a spin-off from Northwestern, and we worked with folks at Thermocalc who are doing database development on these systems. And the general approach to build one of these databases or expand one of the databases is do the initial development with an understanding of what the phase equilibria in the systems are. But you can't get that complete understanding of a 6-component system. And so the initial development is based on binary and ternary systems, and then you extrapolate to the higher order systems. And to validate how well that was working in this case, we use the data from this set of experiments that I just showed, and a much broader array of experiments where we compared the behavior in these 4 different representative deposit compositions with a wide range of potential barrier coating oxides, and then measure solubility limits, et cetera, and feed this into the optimization and validation process. And once we had a database that was working well and could reproduce a lot of experiment results, we can then move forward and actually apply this to understand, in a broader context, the behavior of different coating systems. So to finish today, I'll share 2 brief case studies of how we've done this. And our overall goal is to understand how the calcium-silicon ratio and changes in the amount of the other constituents, magnesium, aluminum, iron, in the deposit influence the reactions. And we want to know, do the reactions still consume the melt? And how far might we expect the coating to recede or degrade before the reactions stop? So I'll start with an example from this environmental barrier coating system. And I'll remind you that here we're dealing with rare earth silicate coatings. And what generally happens is when we have this deposit on the surface, it progressively converts the coating to apatite. It has the wrong CTE, which leads to cracking and eventual failure of the coating. So our goal is to minimize the depth of this conversion process for apatite. So we can study this if we say we're going to take a certain amount of deposit and put it on top of a notional coating, and then ask what is the phase equilibrium as the reaction proceeds. Is there still a driving force to form more apatite? Initially, the coating, if we have a small recession depth, the coating dissolves into the melt to saturate the melt with yttrium. As we increase the recession depth, now we see the apatite start to come out. And when we look at the constitution, or the normalized phase content in that reaction layer, we see more and more apatite as the reaction proceeds. We're not really consuming the liquid at all. It's basically an exchange of silicate and calcium from the coating material to form the apatite, but that doesn't consume the liquid at all. But then we eventually get to a point where this yttrium disilicate, which is the coating material, where silicate shows up as an equilibrium phase. And we can basically draw a line here and say when we get to that point in the process, the reaction will probably stop and the coating recession stop. And the key thing that's happening during this process is that the reaction is consuming calcium from the melt to form apatite and rejecting silicon into the melt, and so the calcium-silicon ratio changes. And it drops and drops and drops and drops and drops until we get to the point that we expect the reaction to stop, and then it stays constant in the residual melt. And we can then use this as a parameter to compare the behavior with a variety of different deposits. Before we did that, in order to assess, is this actually the right behavior, we compared our calculation results with data from actual coating recession experiments where they measured the calcium-silicon ratio in the melt as a function of recession depth, and the results agree quite well. When we get down to this threshold indicated by this blue line, the reaction stops. And you go longer and longer times, the melt just sits on the surface and no more reaction takes place, no further reaction. So we can then pick a range of different deposit compositions. I'm showing three here. In this case, they all had similar initial calcium-silicon ratios. And we see that for the most part, they follow similar trends. There are some deviations at the end that have to do with, at the very end of the reaction, we hit some other phase fields that either extend or contract the total amount of recession that happens. But we get a cluster of recession depths that are out here, and these are all pretty bad. So this says that these particularly calcium-rich melts are probably some of the most problematic. If we instead pick a family of very calcium-lean melts, here there's not enough calcium to promote much apatite formation, and our expected maximum recession depths are very small. So we might lose a little bit of the coating, but not very much of the coating. And then we can kind of fill in between and find that while there is variation within each of these groups, the calcium-silicon ratio in the deposit is an important factor. And we can pick out a few of these, maybe one that shows almost no recession and one that shows a lot of this detrimental reaction or recession process to verify this process experimentally. And so we pick these three different representative deposit compositions and in fact find that this scenario where we expected no apatite to form, we get almost no recession, and that as we increase the amount of calcium in the deposit, the amount of recession increases. So here we get a little bit more, and here this is the line roughly of how much of the coating has been consumed by this process. And if we keep in mind that these coatings are usually only a few hundred microns thick, this is most of a coating in 4 hours. So obviously this is a particularly aggressive case. But if, from a design perspective, if we know that the range of compositions that will be ingested in the engine are more silica-rich, the coating might survive. And so what we learned from this is the calcium content is really what's driving the reactions and the loss of the coating. And so we have a couple of strategies we can use to potentially design better coatings. One would be to find materials that more actively grab calcium from the melt. The apatite pulls some calcium, but it only has about 12% calcium in it. And so if we could find materials we could put into the coatings that would go out and grab the calcium more efficiently, that would be a benefit. We already saw from the comparison of the material with and without zirconium that if we put some zirconium in, for instance, we can increase the amount of the amount of calcium that goes into the apatite, and that might help us. Or we could look for systems that just have a lower driving force to form apatite. So if we go back to this idea that as we change the rare earth cation radius, the driving force for apatite crystallization changes, maybe we pick a rare earth that has the right radius to really limit the amount of apatite or the stability of apatite, and that might help us in a similar fashion. So I'll also share a brief case study looking at this other problem where our goal in the case of the segmented thermal barrier coatings is to limit the amount of penetration that we get into the coating. We want to maximize the amount of material that's crystallized for each mole of coating that dissolves into the system. And we'll ask similar questions about the role of melt composition, as well as try to make a comparison between, in this case, the gadolinium and the yttriate-based systems in the context of the broader range of deposit compositions. So in these materials, we have a pretty wide design space in the sense that the traditional thermal barrier coatings are over in this area. We've got a large solid solution field here, this fluoride phase, we've got this line compound, and we've got this two-phase field that might also make or be amenable to making coatings. And so our question is going to be, if we pick a certain threshold of coating the solution, maybe we say a certain amount of the coating dissolves into the melt, how does the fraction of phases that crystallize as a result of that reaction change as we change the amount of the rare earth element that's in the coating? And so we might say, if this is our starting point, how much crystalline phase do we get as a result of those reactions? In some cases, because of the solubility of the coating in the melt, we might get less back than we put in. And in other cases, we might promote a lot of crystallization. And we'd like to pick a coating that has a behavior like this, where we promote a lot of crystallization. So we can look at the behavior of yttrium zirconium, TBCs interacting with this somewhat middle of the road melt. And in fact, we find, yes, there's this region in the middle that we don't get much crystallization. If we look at the behavior of the same set of coating materials, though, with a different deposit, this is one that better promotes apatite crystallization, we find that this particular coating material, we're actually, because we crystallize the apatite, we're going to get an increase in volume. But if we do the same calculation, this is the same deposit composition with gadolinium, we see that at roughly the same point in terms of coating composition space, we get a lot more apatite. And so this comparison drives home the point that due to the stronger driving force for apatite crystallization in the gadolinium system, the gadolinium-based coatings offer better performance. And so if we pull these kind of transition curves, which show the amount of crystalline material for a given coating composition, we see that the gadolinium is always higher. But from a design perspective, this is the comparison we need to make. If we have an yttriate-based coating and or gadolinium-based coating, we want to switch to an yttriate-based coating, at what point do we get an equivalent amount of crystallization for the same amount of dissolved material? And we find that we get a significant benefit from adding gadolinium, but from the flip side, if there are reasons that we can't use gadolinium because of compatibility issues with other phases or other materials in this coating stack, if we wanted to take a gadolinium-based coating that had a performance about like this and make it an yttriate-based coating, we'd have to put a lot more yttriate in. And so now we have a tool that we can begin to optimize the cations that we put into the coating system, what the compositions are, etc. And this now opens up a tool that we could use if we want to consider all the potential architectures we could choose for our coating design, which one is going to give us the best reaction behavior to mitigate the degradation. So to summarize the talk today, first about drawing insights from the underlying phase equilibria to understand this problem. We then use that to develop some tools that we can use to assess the relative performance of different coating systems. And looking toward the future, the need is to integrate all of these different processes, including both the reaction processes, the kinetics, with mechanics models to link a given state in the reaction process to the mechanical behavior of the system, or ultimately identify whether a system is likely to fail. I'd also like to come back to this idea that much of this variation in terms of the performance of coating materials that I've talked about today comes back to the fact that the apatite crystal structure accommodates a wide range of ionic substitutions, and by understanding those substitutions, we can better understand the performance of these materials. And then finally, I'd like to acknowledge both the funding for the work I've talked about today, as well as those who have helped along the way. The work we did, groundwater remediation in Kenya, was sponsored by the Metropolitan Water District of Southern California, as well as the Rotary. The work on phase equilibria and modeling was supported by the Office of Naval Research through programs with Quest-Tech, as well as separately funded naval programs. In particular, this is a great undergraduate intern I had a couple of summers ago who helped with a lot of the phase equilibrium studies in terms of preparing compositions and characterizing them. So with that, I'll thank you for your attention and be happy to answer any questions.
I find it interesting that gadolinium and yttrium behave so differently in these oxides and compounds. In the tower systems, they're so similar.
Right.
They're almost identical.
Right.
Size, they're both prevalent. The only difference is you got 4 electrons in gadolinium. But I don't think that should matter in this case.
Yeah, I think it has a lot to do with the ionic radius when they're in one of these ionic oxide materials. And I didn't talk about it all today, but one of the things that we did when we were trying to understand these differences in why some coatings work really well and others, that for exactly the reasons you described, we thought should behave exactly the same way, it didn't work at all. And we dug into the geology literature and found that references or discussion and data on partition coefficients between different rare earth oxides and different crystalline phases. And these are used in the earth science community to help understand the evolution of different rocks, how they form. Because you look at the partitioning, the rare earth partitioning, in very dilute concentrations, but between all of the different minerals in a rock. And that tells you something about the history. But from that, we could see correlations to which compositions were most likely to form apatite versus other competing phases. And in some cases, the trends in partition coefficient between these different phases were 6 orders of magnitude different. It was astounding. In particular, the garnet phase that I talked about very briefly. The small rare earth cation have a strong tendency to partition into garnet phases rather than into the apatite phase. And so the span in garnet partition coefficient between ytterbium and lanthanum was 6 orders of magnitude.
Of course, ytterbium is really sort of not a real rare earth.
So that was, in that case, it was ytterbium, not yttrium.
Yeah.
So, yeah.
So, for some of the applications you have, do you ever get to the point where the oxygen activity changes enough that you have to consider that in the phase equilibrium?
Not in these applications. In particular, I talked at the beginning about the design of the engines a little bit, and because all of this cooling air gets dumped into the system, the oxygen activity stays pretty high. And that's actually a problem in the design of the systems because when you burn, and then you dump a lot of oxygen, a lot of air into the hot gases, and so NOx formation, or nitrous oxide formation, is a big challenge. So from a pollution control perspective, the big driver in reducing the amount of cooling air is reducing the residence time of the hot gases in a high oxygen activity environment that promotes the NOx formation. So in general, it's all pretty oxygen rich.
This apatite precipitation is dictated by the diffusivity in the liquid.
To a very small degree. So there's a graduate student who I'm working with right now, and that's one of the things that he's studying, is to try to work out what is the influence on the difference in diffusivity on the reaction dynamics. And I didn't include anything about work we've done on the dynamics side, but a few years ago we did a bunch of experiments where we did these very short time exposures. In this case, we suspended particles of the thermal barrier oxides in beads of glass, basically, and we could do like 1 minute, 2 minute, 3 minute, 4 minute punch type experiments to start to back out what are the diffusion coefficients for the rare earth oxides. And it turns out that the rare earth diffuses very, very quickly. Where you get some diffusion limitation is that the zirconium is much less soluble and diffuses much more slowly, it has a higher field strength. And as a result, the dissolution is limited by how quickly you can get the zirconia away from the system. But on the precipitation side, the diffusion of the rare earth in the melt doesn't seem to be a limiting factor. But it's a great question you asked. Thank you.
can't imagine that in some extent the design of these coatings is really depending upon the design of the turbine engine itself, right? So do you know if that engine design is projected to change over the next 10, 20 years, and would that affect the kinds of materials that you're studying?
So the driver in the engine design is always toward higher temperature. And so in that case, the coating design can go two ways. One is you make the coatings progressively thicker and thicker on the same substrates. And as you do that, ideally you'd like to find lower thermal conductivity materials to use in the coatings. So when you look at all the design parameters for the coating, there's 10 or 15 different things you're trying to optimize around. The big change, though, that's happening basically as we speak is the conversion of metallic components that require a lot of cooling air to keep them cold to ceramic structures that even if the overall combustion temperature or gas path temperature isn't changing, they require a lot less cooling air. So the newest engines from GE have started incorporating a lot more ceramics into the hot section. They use a lot less cooling air. And so in that sense, the coating design shifts from being one of primarily thermal protection, insulation, to one of environmental protection and preventing the underlying ceramic or composite from degrading. Does that answer your question?
Do we have questions? All right. Let's thank the speaker again.